Okay, people. So, assignment 3 due middle of next week. Solutions to assignment 2 are out. Of course, they're under week 4, under where the assignment lives. Good time of the semester to start thinking about whether there are things you don't understand, and if you have questions to ask, remember my contact hours, the MLC, the forums, everything else. Okay. So, I think we've got 3 fun things for you today, I think. So we've got Pascal's triangle, we've got the binomial theorem, and we've got the principle of inclusion-exclusion, and they all sort of tie into Pascal's triangle. They are all related, so fun stuff. Okay, so you can, if you want to, write the binomial coefficients. So remember, we learned about these. These are the n choose r things. And you can write them in this sort of a pattern if you want to, right? So we have on the 0th row the 0 coefficients. On the first row, 1 choose 0 and 1 choose 1. On the second row, 2 choose 0, 2 choose 1, 2 choose 2, and so on, right? Here are all the 6 choose somethings along the 6th row, if you like. So you can do this, but I guess the question is, why would you want to? And one reason is it makes a kind of cool-looking pattern. But we're going to see some reasons beyond just this looks cool. So this is usually, most often in the Western world, it's called Pascal's triangle. Pascal was nowhere near the first to come up with this. The best defense for calling it Pascal's triangle is maybe he was the first to be silly enough to write an entire book on it, so maybe that qualified him in some way. If you're looking for when these ideas first emerged, the Indians were really early on to this. So you're talking people like Pingala in the 3rd century. But also long predating Pascal, we had Chinese and Persian mathematicians. So in China, this is Yang Hui's triangle, forgive my Mandarin. If you go to Italy, there's an Italian chap they name it after. He starts with a T, but I've forgotten his name. Omar Khayyam mentioned this, but he wasn't the first Persian to come up with it. Anyhow, long history before Pascal, but it usually goes by Pascal's triangle. So this is one of the early Indian manuscripts with the triangle in it. So you can see it's arranged slightly differently, but still a triangle going on. Okay, so there's a bunch of patterns in this. We're going to talk about 2 of them. Does anyone care to name me a pattern? Who wants to pick something about this triangle that's notable?
The first half, apart from the second half, minus the middle element if there's any in it or the same.
Yes, okay, I totally agree. So if you take any row and you reflect it left to right, you get the same thing, right? The rows go up and then down again. 1, 6, 15, 20, 15, 6, 1. 1, 3, 3, 1. Yep, so that's one of the patterns we're going to look at, in fact. Any other fun things? So the idea being that everything is the sum, everything internal is the sum of the 2 things sort of on top of it? Yes, okay, so I did not plant those answers, but those are in fact the 2 properties we're going to talk about. So one is that every row reads the same forwards and backwards. The second is that everything is the sum of the two things on top of it, everything that's inside, right? So let's talk about those. So the first one is that every row reads the same left to right and right to left. And this is the same as saying that n choose r is the same as n choose n minus r, right? For any r between 0 and n, right? So I've got some stupid team selection analogies for this. So you're picking a starting team of 11 players from a squad of 15 players. Say you're a youth coach or something, right? You've got to pick 11 of the kids to play and 4 to sit on the bench. So if you're, a reasonably sensitive human being or something, maybe you read out the 11 names and you say, you've all made the starting team, well done. And then you say, for everyone else, you tried really hard, you'll be sitting on the bench to start with, but you'll make an impact when we bring you in later, right? But of course, if you're more of an asshole, then you can say, right, you 4 people, you're failures, go sit on the bench, everyone else, you're starting, right? And I agree there's perhaps a moral difference between those two approaches, but they are conveying the same information, right? Saying these 11 are in, if there's 15 things in total, is the same as saying these 4 are out. So choosing the 11 is the same as choosing the 4 that are out. And so this, it's 2 different ways of expressing the same choice. There's got to be the same number of ways to do each of them, right? Same number of ways to pick 11 starters as there are to pick 4 on the bench to begin with, right? So 15 choose 11 has to be 15 choose 4, and that wasn't anything specific about 11 and 15, right? It's true in general. So choosing R things to go in a set is the same as choosing N minus R things to stay out of a set. Does that make sense to everyone? And so that tells you that our triangle is going to read the same forwards and backwards, right? Because we've got, for example, here is 6 choose 1, here is 6 choose 5. Choosing the 1 thing to be in is the same as choosing the 5 things to be out. Making sense? Cool. Okay, good. I think this is a copy of Yang Hui's manuscript. Using rod numerals, if you're a, I don't know, a Chinese numerical history nerd. Okay, so the pattern that takes a little bit longer to think about is this: everything is the sum of the 2 things on top of it, right? And so, for example, we have things like 6 choose 2 is 5 choose 2 plus 5 choose 1. That's saying 6 choose 2 is the sum of the 2 things on top of it. So I've got a different stupid team selection analogy here. Again, you're picking a starting team of 11 players from a squad of 15 players. But say now you're the, coach of a, I don't know, community football team or something. And you've got a particular, sometimes star, sometimes nothing, call him Bob, right? And sometimes Bob shows up before a game and he's lightning fast and he's putting everything in the corner of the net, and you think, today Bob is definitely playing, right? And other times Bob shows up before a game and you can still smell the alcohol on his breath from last night, and he's sort of stumbling around and whatever else, and you think, Bob's definitely not playing today, right? So, if it's one of the latter days, if Bob's not looking good this morning, then you're basically down to 14, choose 11, right? Because Bob's out, you know you're not playing him. So you've got your other 14 and you've got to choose 11 starters there, right? And if Bob is definitely playing, if he's really on today, then you're actually at 14, choose 10, right? Because Bob's definitely in the team, so you're only picking 10 others, and you've got the rest of the 14 to select from. Make sense? Right? So, this is the number of ways to pick a team without Bob. This is the number of ways to pick a team with Bob. But of course, the addition principle tells us that the number of ways to pick a team total has to be the number of ways to pick a team without Bob plus the number of ways to pick a team with Bob. And we know the total number of ways to pick a team is 15, choose 11, right? So that means 15, choose 11 has to be 14, choose 11 plus 14, choose 10. Does that make sense? Right? Total number of teams is total number of Bob teams plus total number of non-Bob teams. And of course, there's nothing magical about 15 or 11 or about calling one of your elements of your set Bob, right? All of this argument goes through in general, right? You just think about pick an arbitrary element X of your set, think about the ways to choose your set with X, think about the ways to choose your set without X, and you get this thing here. So in general, n choose R is n minus 1 choose R plus n minus 1 choose R minus 1, because this is the number of ways to choose the set without a specified thing X. This is the number of ways to choose it with X. Does that make sense? Okay, so those are our two patterns, right? We've got that every row reads the same left to right and right to left, and we've got that everything is the sum of the two things on top of it, right? It sort of looks like these won't quite be on top of it, like this will be on top and this will be to the right, but remember, because the triangle's a triangle, not looking like that, they are the two things sitting on top of it. Okay, how are we going? All right, so any questions on that? I went through that a bit quicker than I was expecting. Is that really making sense to people? Cool. Okay. So, without looking back at your notes or whatever, tell me, what is 0, choose 0? So, there's a couple of ways you could think about this. You could think about the definition in terms of factorials. That'd be one way. You could think about Pascal's triangle if you wanted to. You could also think about this philosophically if you liked, and see if your answer to what should 0, choose 0 be lines up with things. So I'll give you a minute to discuss and whatever. Even if you're confident of the answer, decide if you think it actually makes sense or not, or if it's just one of those weird maths, yeah, this is just this because there's things. How are we going? Good, okay. So, the perhaps easiest way to think about this is, remember Pascal's triangle is bordered by ones, right? So 0, choose 0 is the thing at the very tip of the triangle. It's the top, it's a 1. But there's some different ways to think about this. You can also think of it when you use the definition of n choose r in terms of factorials. That's n factorial divided by r factorial times n minus r factorial, which in this case would be 0 factorial divided by 0 factorial times 0 factorial. And remember, 0 factorial, one of those weird things, turns out to be 1, so that's 1 on 1 times 1, which is 1. I think you can almost make a case for this philosophically as well, right? If you think about choosing 0 things from a set of nothing, you can do that. You do it by choosing nothing, and there's only sort of one way to do nothing. But whether you believe that or not, I don't know. But anyhow, the other two are probably good enough reasons to do this like this. So 0 choose 0 is 1. And in fact, of course, n choose n is 1 for any n, right? Okay. So that was our first look at Pascal's triangle. We now want to look at something that relates to it very heavily, which is the binomial theorem. So binomial, in this case, means something that looks like this, right? Think about something plus something to the power of something, right? So here, I've written down x plus y to the power 0, x plus y to the power 1, x plus y to the power 2, x plus y to the power 3, and so on. And hopefully, you can see I'm getting Pascal's triangle here as the coefficients, right? So this is 1, this is 1, and this is 1. This is 1, 2, 1. This is 1, 3, 3, 1. This is 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. That's Pascal's triangle back again, right? So, first question is why? Why are we getting Pascal's triangle like this? And the answer is sort of, if you learned it with an acronym, when you were in year 9 or 10 and learning to multiply, you know, x plus y times a plus b, was FOIL the acronym? First, outside, inside, last? There's various acronyms, but say it was FOIL. So the general version of that says, how do I multiply, for example, x plus y times x plus y times x plus y? Well, I go through every single combination, right? That first outside, inside, last is really just saying do every combination, right? And the same happens here, right? So you try and do it systematically, x times x plus x times y plus x times y times x plus x times y times y plus, where am I up to? Y times x plus, and so on, right? You just go through systematically choosing every possible combination of x and y at each time, right? So then, when you think about it, let's think about this term here. Why does this have a 3 in front of it? Well, how many times do we get something that boils down to xy squared? right? Well, we can get that three ways, right? We can choose our x here and our y here and our y here, and we get an xy squared. Or we can choose our y here, x here, y here. That's yxy, which becomes an xy squared. Or we can choose our y here, x here. That's yx, which becomes an xy squared. Right? So those are the three ways we get xy squared, which is why this is a 3. And you think about that, why is it that? Well, we had to choose one x out of 3 possible places. We could choose an x, right? And if you think about this in general, if I had 5 of these here and I was looking for my x squared y cubed term, then I'd be choosing 2 x's out of 5. That would be 5 choose 2, which is why this term here is a 10, right? 5 choose 2 is 10. Right, so that's why I'm getting this pattern. It has to happen that way. It's not just a fluke. I have to get this Pascal's triangle back as the coefficients of my binomials. And so that leads us, does that make sense? Good. Okay. That leads us to something called the binomial theorem. I had to squash it in a bit in the notes, so let me give you the single line version here. What it says is that if you're expanding out x plus y to the power n, then you want, so basically your coefficients are going to be the rows of Pascal's triangle, right? So each term looks like this. It looks like n choose I, x to the power of n minus y, x to the power of n minus I, y to the power of I. Right, so of course my powers of x and y always have to add up to n because I'm choosing I y's and n minus I x's. But the key thing this is telling us is that the coefficient here is always n choose I, right? So for example, I get n choose 2, x to the n minus 2, y squared. Does that make sense? So that's the formal mathematical way of writing out the coefficients come from Pascal's triangle, right? So it turns out that with the binomial theorem, we can prove a bunch of other sort of cool patterns about Pascal's triangle just by making some substitutions. So the notes tell us how to do a couple of these, the questions in the notes. So let's sub in x equals 1 and y equals -1 into our statement here, right? Because remember, this holds for any real numbers x and y. Right, so I'm just going to choose x to be 1, I'm going to choose y to be -1. So what does this left-hand side become? 0. There's one tiny caveat to that, but basically it becomes 0. I'm going to talk about that in a second. It becomes 0 to the power n. Okay, now let's think about what happens here. So I'm going to get 1 to some power and -1 to some other power here. So at first it's going to be 1 to the n, -1 to the 0, that's going to be 1. Then it's going to be 1 to the n minus 1, always 1, -1 to the 1, that's going to be -1, right? Then it's going to be some number of 1s times -1 squared, that's going to be +1, and so on, right? I'm going to swap signs along my row. So what I get is actually just my row of Pascal's triangle, but added up with the signs alternating, right? So I get the first thing in Pascal's triangle in the row minus the second thing plus the third thing minus the fourth thing plus the fifth thing, and then at the end it'll be a plus or minus depending on which row I'm in, right? Whether it had an odd or even number of things in it. But remember, this is 1 minus 1 to the power n, right? So this is 0. And so this tells me that if I take any row of Pascal's triangle and I start by adding and then subtract and then add and then subtract and then add and then subtract, I will get 0 back. And that sort of follows from the fact that these rows are reflections of each other, right, if you think about it. There is one important caveat to this. 1 minus 1 to the n is 0 for any n except n equals 0, right? Because 0 to the 0 is technically 1, and that's why the very first row here adds to 1, right? This pattern doesn't hold for the first row of Pascal's triangle because it is just a 1, right? But everything else, you do the alternating sum, you get 0. Okay, so how about we do a different thing? How about we do this with 1 and 1 instead, right? We did it with 1 and -1 before, x equals 1, y equals -1. Let's do it with 1 and 1. So if I sub in x equals 1 and y equals 1, then my left-hand side is going to become 2 to the power n, right? And all of these terms is just some number of 1s times some number of 1s, right? So everything just drops down to, the sum from the row of Pascal's triangle, and I find that the sum of the nth row of Pascal's triangle, remembering we call the first one the 0th one, the top row the 0th one, is just 2 to the power n. So why should this be? Why does this make sense? Yeah, so I think that's sort of right. Like every combination. So, okay, think of it like this, right? You go to a pizza store and they have n possible toppings, and the guy says, look, you can choose just any combination of these. We have no limits, right? You can choose any possible combination of toppings. It all costs the same. We don't care, right? So one way to count the number of things you can do is just to say, well, every topping I can say yes or no to, right? So that's 2 to the n, right? He names you the first topping, you say yes or no. He names you the second topping, you say yes or no. You go through right to the end, 2 to the n, right? But of course, you can count the number of things you can do in another way, right? Firstly, you could say, no toppings please, just give me some hot dough, right? And there's one way to do that. Or you could say, I'm only going to have one topping, despite your incredible generosity, just olives, right? And there's n ways you can do that, because there's n toppings. Or you could have 2. Or you could have so and so and so and so on, all the way up to you could have n, right? And that's got to, again, be the same thing, right? It's the same choice, right? for any combination of toppings, you've either chosen 0, 1, or 2, or 3, or all the way up to n. So you add up all those possibilities, and you get the total number of choices. So hopefully this makes sense, right? Another way of thinking about this is the size of the power set of a set of size n. This is the number of, well, sets of size 0 in that power set, just one, just the empty set. This is the number of sets of size 1. This is the number of sets of size 2, all the way up, right? Okay. Does that make sense? Okay, so deceptively simple question coming up. Deceptively simple question that was written in 2021, I think. So this is just asking, after I do the expansion and simplify in the binomial, how many terms are there in the sum, right? Going to make this a fairly quick one, so have a quick chat to your neighbour, make a decision. Okay, another 20 seconds. Okay, good. So, excellent. We get one more than the power because when you think about it, I'm going to get every power of x between x to the 0 and x to the 2021. Obviously, every power of y in the same backwards. And there's 2022 numbers in there. So D is our answer there. Good stuff. Okay, and this was actually Pascal's diagram, so we've finally gotten onto Pascal. Okay, so last big idea for this lecture is another really cool thing called the principle of inclusion-exclusion. And so it's a way of counting the size of a union of sets. So the example in the notes is if a school gives out prizes to the 10 best music students and the 8 best art students, then if there's 3 students that receive prizes in both, right, you've got these 3 overachieving nerds, then if you sort of think to yourself how many students got prizes and you say 10 plus 8, then you've overcounted, right? Because you've counted the 3 overachievers twice, right? So to get back to the right answer, you need to subtract away those 3, right? Subtract the overcount. And so this tells you that if you are counting the number of things in A union B, then it's only going to be size of A plus size of B if the sets are disjoint, if they have no intersection. Otherwise, you have to remember to subtract away the things you've counted twice, which are exactly the things in both, right? And there's a more complicated version for 3, but let's talk about why that works. So for 2, the situation looks like this. If I count the number of things in A and add it to the number of things in B, then I get this situation, right? The things out here, I'm right on. I've counted them once. The things out here, I'm right on. I've counted them once. But the things in here, I've counted twice, right? They got counted as part of A and as part of B. So then, if I give this little robot a mouth, if I subtract away this size, the size of this intersection, then I'm right? Now I have counted everything here once, everything here once, and everything here 2 times minus 1 time is once, right? So that's for 2. Now let's talk about 3. So what I can do for 3 is this. I'm going to add up the sizes of the sets. And when I do that, I've counted everything here once, everything here once, everything here once. So I'm right on the outsides. But the stuff in here got counted twice, and the stuff in here got counted twice, and the stuff in here got counted twice, and the stuff in here got counted 3 times, right? So now what I'm going to do is I'm going to subtract away the sizes of the 2-way intersections, right? So I'm going to subtract this size here, and this size here, and this size here. And what happens then? Well, I subtract away 1 here, so this is plus, plus, minus. This is now correct, right? Which is why I did this. This is plus, plus, minus. This is correct. This is plus, plus, minus. This is correct. But I subtracted this middle 3 times now, right? So I've gone from counting it 3 times to now I'm back to counting it 0. But it's the only thing I'm wrong in, so what do? I add the size of the middle 3-way intersection back again, and finally I'm correct, right? Everything here now has been counted in net total once. And so this, and that is, if I flip back, that is this thing here, right? Size of A plus size of B plus size of C minus the 2-way intersections plus the 3-way intersection. And it turns out that this works in general. Even though it starts getting hard to draw Venn diagrams, what you can do is to find the size of any union of sets, x1 to xt, you first add the sizes, then you subtract the sizes of the 2-way intersections, right? Then you add the sizes of the 3-way intersections, so intersections of 3 sets. Then you subtract the sizes of the 4-way intersections, all the way down to, depending if there's an odd number or an even number, you'll either add the t-way intersection, the unique very middle of your Venn diagram, or you subtract it, depending on whether your number of sets is odd or even. And this is something you might have to go away and think about. But the reason this works is also because of Pascal's triangle, right? So if you think of any element, it's going to be in n of the sets, right? Where n is some number between 1 and t. Could be in all of them in t, could be in just 1, could be in 7 or whatever. But when you think about it, the number of sets where it's going to be counted in the first bit of this, where we add the sizes of the sets, is n choose 1. It's going to be counted n times, right? Because it's in n of the sets. Then, when we subtract the 2-way intersections, there's going to be n choose 2 of them in which this thing is subtracted, right? Because it's in n sets, there's n choose 2 ways of choosing 2 of those sets. And then it's going to be added n choose 3 times in the 3-way intersections and subtracted n choose 4 times in the 4-way intersections, and so on, up to added or subtracted n choose n times. And this is an alternating sum along the row of Pascal's triangle, except it's missing the very first term. And so if you go back to what we were saying about the alternating sums being 0, except this one is missing what would be effectively a -1, it turns out this is going to equal 1, and so overall we have counted this once. In other words, in terms of these diagrams, we got n choose 1 pluses, n choose 2 minuses, n choose 3 pluses, n choose 4 minuses, and so on, and then on net, that magically, or because of Pascal's magic or Pingalu's magic or whatever, comes out to be 1, right? So that's why that works. Questions on that? We do have a second. That's one of those things, like that's tricky. You know, when I was preparing this lecture, I had to sit down and remind myself of how that worked. It takes a little while to think your way through, but worth doing. It's nice. Okay, so this is one final example of using inclusion-exclusion to count something that is not obvious how to count, right? So if someone asks you how many numbers between 1 and 100 are divisible by 2 or 3 or 5, it sort of seems like that's something where you just want to write a computer program and ask it, right? Or just go through, write down a big old list of numbers and tick off the ones, right? You know, it sort of seems like a pain. But it turns out you can do it in a reasonably non-painful way using inclusion-exclusion. So let's think of x2 as the set of numbers divisible by 2 between 1 and 100. x3 is the set of numbers divisible by 3 between 1 and 100. And x5 is the set of numbers divisible by 5 between 1 and 100. And these are pretty easy to count now, right? Because I know there's going to be 50 of these. If you think a little bit harder, there's going to be 33 of these, and there's going to be 20 of these. So now I'm interested in x2 union x3 union x5, all the things that are divisible by 2 or 3 or 5, or more than one of them. And I can use principle of inclusion-exclusion, right, which is sometimes PIE. And it tells me this: add the sizes of the sets, subtract the 2-way sizes, add the 3-ways. Sorry, subtract the 2-way intersection sizes, add the 3-way intersection size. And now, I told you how to count x2, x3, x5. These ones are not so hard to count either, because x2 intersect x3 is counting the numbers that are divisible by 6. This is counting the numbers of which are divisible by 10. This is counting the numbers that are divisible by 15. You've still got to think, I'm not saying this is entirely pain-free, but at the end of the day, you get 50 plus 33 plus 20. That was our sizes of these. Sizes of our 2-way intersections wind up being 16, 10, and 6. And the size of our 3-way intersection, that's the things that are divisible by 30, is just 3. Turns out it's 74, so perhaps unsurprisingly it's most of them, right? So, yep, just a final example of a way to use this to do a count that at first looks like it might just be a slog, right? Okay, that's all I have for you people. Tomorrow we're going to start looking at probability, so that should be fun too. Hey.
Can I ask for this bit of the notes where it talks about how it's the sum of the two things above?
Yep.
Should it include n as the upper limit? Because I think it should exclude it. Because you see, it doesn't include 0. And if you include
Yeah, so that's a good point. I think I probably meant for it not to, but let me just think. So, by convention, n minus 1 choose n is 0, right? There's no way to choose n things from n minus 1. And n minus 1 choose n minus 1 would be 1, and n choose n would be 1. So it does technically still work, but I think I was trying to, when I wrote this, avoid tricky things like this. So I think I probably meant to stop it at n minus 1, because it really is talking about internal things. So I will try and remember to fix that up, thank you. But it does still technically work there. Yeah. Thank you. Yeah.
Hi, Mr. Horsley. I just had a question about assignment 2.
Uh-huh.
See if I can even find it. Okay. Yep. Here we go. I got marked down from my induction, mainly because there was something wrong with my P of N statement.
Yeah, so P of n
Yeah.
shouldn't include for n greater than or equal to 1.
But what's wrong with including it?
Well, because this has to be a statement about, like, if you'd closed your quotes here, that would have been okay.
Yeah, but I was just trying to
But-
be more specific with my P of N statement.
Well, but you see, if you'd closed the quotes here, that'd be okay, because then you'd be saying P of n is this statement,
Yeah.
and I'm defining this at P of n for each n greater than or equal to 1.
Yeah.
But like here, you're saying that P of 7 is this thing for 7 greater than or equal to 1, right? Like it has to be a statement about a specific n.
Yeah.
So we are being pretty tough on the nitty gritty of this because it's whatever. So yeah, that's what's going on there.
Yeah, and then so I did that, and I did the same thing for question 2. So I think I've got a satisfactory answer for that. And I think, let me see if I can open it up. But I lost another mark in my strong induction. I think there was something wrong with the way I wrote it. Yeah. So go to 2.3. So it says this is what the marker has written. So K is defined.
Above as being some number between 1 and
I think it was somewhere here. That's where he marked it wrong.
Yeah, so I mean, this step does not work for k equals 1, right? Because you say ak plus 1 equals this. That isn't true for k equals 1. That'd be a2 equals 5a1 minus 6a0, where a0 isn't defined, right? This only holds where this is at least a 3.
Yeah, and then I wrote that here.
Yeah, but you're saying here, assume P of k is true for k greater than or equal to 1 and k less than.
I did it for k greater than or equal to 1 because I thought k replaces n. And then we move to 3 because we proved the base cases that it's true for n equals 1 and n equals 2.
Yeah, well, in that case, what you'd need to do is you'd need to say here where n is greater than or equal to 2, right? Because I need to justify that.
Yeah, I think that's what he said. Okay.
Yeah,
But like,
Right,
why
so-
do I need to say n greater than or equal to 2?
because this step doesn't work if you only assume P of 1, right?
Okay.
right? So at the moment, you've got this n floating around that I don't really know what it is. You've got to nail that down.
Yeah, okay. So it's just really small things, I guess.
Well, they're important though, right? Like that sort of thing. Like,
Yeah.
like they really are.